Alright, here is 7.1 notes. We're doing absolute value functions and their transformations. So first thing we need to remember is what absolute value is. The absolute value is the distance from 0. So for example, if I have the absolute value of -3, we know that the answer to that is +3 because the distance from 0 is 3. So for now we're going to focus on the graphs of absolute value functions. So here is our parent function. Our parent function just means that's the original. Nothing has been done to it. This is the one we are going to compare every single function to when we graph it. And we can actually write this absolute value function in this form. This is called a piecewise defined function, and we are going to do more of these later. But for now, we'll just talk about what it means. So this just means that I have different pieces to this same function. This function is broken into two pieces. One piece, I have the function x, if I'm looking at x values that are greater than or equal to 0. The other piece is -x, if my x values are less than 0. So we're going to use these to find the values in our table to be able to graph our parent function. Alright, so first I have an x value of -3. Well, that falls into this function here. Because x is less than 0, it's -3. So I'm going to take my x value and plug it in for x in this function, -x. So that will give me -3. Well, minus the negative is a positive. So that's my y value. If I have a -2, that is still less than 0. So I'm going to take that x value and plug it into this function, -x. So I'll have -2, and that gives me +2. Then we have -1, that is still less than 0. So I'm still going to use the function -x. So I have -1, that gives me an x value, or a y value of 1. Now 0. This one we have to be more careful. Which of these includes 0? It is the top one. So because 0 is included here, we're just going to plug 0 in for x. Well, if I replace 0 with x, then my y value is 0. Because this is the same as having y equals x if x is greater than or equal to 0, and this is the same as having y equals -x. So we're taking our x values and we're plugging them in to find our y values. So back to our table, we have 1. 1 is greater than or equal to 0, so I'm going to plug that in for x, and that gives me an x value of 1. I have 2. I'm going to plug in 2 for x. When I do that, I get y equals 2. And then same with 3. I'm going to plug in 3 for x. When I do that, I get my y value of 3. So I have my table. I used my piecewise defined function to find my table. Now let's graph it and see what absolute value functions look like. So I've got -3, +3, -2, 2, -1, 1, 0, 0, +1, 1, +2, 2, and +3, +3. So whenever I graph an absolute value function, it is going to give me some type of V shape. And this is our parent function. So our parent function, again, is the one we're going to compare all of our other functions to. This place where those two lines come together is called our vertex, and that's going to be very important. So let's look at our table real quick. Let's look at that vertex. My vertex is 0, 0. Notice what's happening at the numbers around it. They are mirroring each other. 0, 1, 2, 3. That won't always happen exactly, but that we can almost always look for that to find where our vertex is. Alright, so that is our vertex. Here's what our parent function looks like. Last thing is domain and range. I want us to look at this in two different forms. In set builder notation, and in interval notation. These are notations we have already learned. We just need to remember how to use them. So remember, for our domain, we're always looking at our x values, looking side to side. Well, on my left, the x's are going on and on forever because of that arrow. On the right, they're going on and on forever. So my domain here is all real numbers. How do we write that in interval notation? We are going from something to something in interval. We're going from -infinity to infinity. Now we want our range of both of them. For our range of this function, we look at the y values. So our vertex is always either going to give us a minimum value or a maximum value, because sometimes our v will open down. So our minimum value here, our lowest number, is 0. That's our lowest y value, and our numbers are getting bigger from there. The y values are getting bigger. So we're going to have y as an element of the reals such that, because this is a continuous function, well, such that y is greater than or equal to 0, because our y numbers, or our y values, start at 0 and they are getting greater. Our y values are going up. How do we put that in interval notation? I just start at the bottom. The first thing I hit is 0, and I have a closed circle there, so it is included. And then I keep on going, and the next thing I hit is those arrows, and those are heading up forever to infinity. So it's from 0 to infinity. We're going to practice both of these notations on the back. And one thing to notice is that the domain for absolute value functions will always be all real numbers, because we will always have a v opening up or a v opening down. So it'll always be all real numbers. Let's go ahead and graph 2 more using tables, and then we'll actually look at another method for graphing, which is using the transformations. All right, here we go. So let's graph using a table. I'm going to give you the x values, and then we'll find those y values together. So let's use 0, 1, 2, 3, and 4. Well, to find our y values, we're going to take our x, and we're going to plug it in for x into our function to get the y values. So if I plug in 0 for x, I'm going to have the absolute value of 0 minus 2. Well, 0 minus 2 gives me the absolute value of negative 2, and the absolute value of negative 2 is 2. So that's how we find our y values, or the f of x values. We're going to go plug them in. So take your x value of 1. If I plug in 1 for x, I've got the absolute value of 1 minus 2. Well, 1 minus 2 gives me negative 1. So I have the absolute value of negative 1 is positive 1. I'm going to plug in 2. I've got the absolute value of 2 minus 2. Well, that gives me the absolute value of 0, which of course is just 0. Now I have 3. I have the absolute value of 3 minus 2. 3 minus 2 gives me the absolute value of 1, and the absolute value of 1 is 1. Then I have 4, so the absolute value of 4 minus 2, and the 4 minus 2 gives me 2, so the absolute value of 2 is 2. So there's my table. I took all my x's, I plugged them in for x to find the y value. And now let's graph it. So I'm going to go to 0, 2, 1, 1, 2, 0, 3, 1, and 4, 2. So here is my absolute value function. We always connect our lines because this is continuous. This is a continuous function. There's nothing about it that says discrete. So that means we always connect our dots with arrows going forever and ever in both directions. So let's look at this real quick and identify our vertex. So remember, the vertex is wherever those two lines come together, because these are two separate equations and they come together at this vertex. There's our vertex on our table to 0. And then real quick, let's compare this to the one we graphed above it, the parent function. So we graphed the parent function here, and again, this is the one we'll compare them all to. Notice where the vertex is at 0, 0. Well, if our parent function usually has a vertex of 0, 0, what happened to get from the parent function to our new function? We went to the right 2 places. So we actually went right 2. And let's look at our function. What do you see in our function? I see a negative 2 there. That is connected, and we are going to talk about that in a bit. So let's look at the next example, and then we'll talk about transformations. All right, so on this, we need to find our y values. So let me give you the x's. We want negative 3, negative 2, negative 1, 0, and 1. Take a second and pause the video and find your y values. Okay, now that you've found the y values, let's check them with mine. I have my y values filled in and I showed you how I got them. Just as a reminder, we took our x's, we plugged it in for x, and then we solved it to get our y values. So let's go ahead and graph it. I'm going to go to -3, 0, to -2, -1, -1, -2, 0, -1, and 1, 0. So here is my absolute value function, the graph of this one. So let's talk about it real quick. Look at that vertex. Here is our vertex, and that is -1, -2 in our table. So let's talk about the parent function. Remember, the parent function is always found at, it starts at 0, 0. So if I'm going from 0, 0 to my new function, where did we go? Well, we started out by going left 1. We went left 1, and then we went down 2 to get from the parent function to the new function. We went left 1, and we went down 2. Well, look in our function, and what do you see? We went left 1, and I see a positive 1. We went down 2, and out at the end I see a -2. So those are connected, and that's what we're going to talk about now. After this point, we're not going to use tables to graph these. We're going to use the transformations of the function. So let's remember what the parent function is. We know that the parent function is y equals the absolute value of x. That's our parent function. Now the function that we're going to use from now on is the transformations of the parent function. So if I'm given any absolute value function, we will be able to graph it using this. Y equals a times the absolute value of x minus h, and then on the outside plus k. That's the transformations of the parent function. That is something that'll be really helpful for you to memorize. That's going to be really helpful. That's the transformations. So now we're going to talk about 4 specific transformations that happen and how we can find them in that function. Our first transformation is the reflection. So if something is reflected, that means it's flipped over the x-axis or the y-axis. So in our case, we're just going to be focusing on the x-axis. So if I have a reflection, I'm going to look at that a value. So if the sign for a is negative, that means we have a reflection. Sign for a is negative means we have a reflection. And if we have a reflection, that means our graph, our V, is going to face down. It's going to open downward. So that's what a reflection is. That's how we find it. Let's look at vertical stretch and shrink. So a stretch actually means that the graph gets narrower. So let's draw a line there. If our graph is stretched, that means it gets narrower. So our V is actually going to be taller and thinner. It's going to get narrower. So I think of stretching our graph up. If we have our function, we are stretching it up. So that's going to get narrower. Well, the way to figure that out is also by looking at the a value. If the absolute value of the a value is greater than 1, that means it's a stretch. The reason we say absolute value here is because if we have a negative a, that negative only tells us a reflection. It doesn't tell us anything about the stretch or shrink. The only thing about the stretch or shrink is what that actual a value is. So if it's bigger than 1, then it's a stretch. And then if that a value is less than 1, it is a shrink. So when we shrink it, it's actually going to widen our graph, which means it's going to get shorter and wider, okay? So I just think of pressing down, compressing our graph, and if we compress it, it's going to get shorter and wider. If you'll head over to the next video, we will finish up these transformations.